Last time we introduced the notion of work and talked about the concepts and the ideas behind it. As you'll remember, in physics, work is the line integral of the force. It's defined to be the integral of F dot ds. In physics, work is done by a force as that force acts on a moving object. What I want to do today is to look at some examples involving work and the kinetic energy theorem. The most common case that we'll encounter in this course deals with constant forces. That is, a force that has the same magnitude and the same direction. So what I'm going to do here is rewrite this expression for the work in the case where the force is constant. It's important to remember that this constant force means both the magnitude and direction are constant. If either one of those are not constant, you need to come back up here and evaluate this expression instead. So this is both magnitude and direction constant. All right, before we rewrite the expression for work, let's look at a case where this might happen. Suppose we are pushing a shopping cart. So the shopping cart looks something like this. There it is. And we're going to walk along and push this thing. And the pushing force that we're exerting, I'll call F, we're going to imagine that that force has the same magnitude. We're always pushing as hard on the cart, and we're pushing it in a straight line. So the direction of the force is constant also. Now if the force is constant, if this is constant, we can drag it out of the integral, and what we get is the force dotted into the integral of ds. The integral of ds tells us to add up all of the little line elements forming the path. So we can suppose if the cart moved from here over to here somewhere, then as the cart moves, all of these little vectors that I'm drawing are the ds elements, the elements of the path. So each of these would be a ds. And the integral tells us really just to add them all up. So that would give us a vector that goes from the beginning of the first one to the end of the last one. And that is the vector that, when we were defining kinematic quantities, we called the displacement. So this integral of ds is just the displacement, delta r. So when the force is constant, you can write the work done by that force as the force dotted into the displacement. If you use our definition of dot product, magnitude of the first times magnitude of the second times cosine of the angle between them, you can rewrite this as F times delta R times cosine of phi. You can also rewrite it as the x component of the first vector times the x component of the second, plus the y components multiplied, and so forth. So if the force is constant, here are three ways to rewrite the expression for how to calculate work. It's the force dotted into the displacement, which can be written any of these ways. All right, so let's take these expressions for work and do some examples. I want to show you three cases, and in each of them, we'll calculate the work done by a couple of forces. Now, for the first case, let's suppose that we have somebody holding a baseball. So here they are. Here's a person. Here's their hand, and in their hand is a baseball. They're going to be supporting the baseball, so they'll be exerting a force F in the upward direction. So the force F is up like this. They're supporting the baseball in their hand. And what they're going to do is lift this baseball up. So I'm going to draw in red a displacement. They lift the baseball up as high as they can so that the baseball moves in the direction that the force is. Now, if the force F is parallel to the displacement delta R, then this angle phi is 0 and the work is positive. In this case, the force exerted by the person is doing a positive work on the baseball, tending to speed it up because that dot product is positive. Okay, now second case. Let's assume that, let me draw their head a little smaller. Let's assume that the person has lifted the baseball up as high as they can. So here it is at the very top. All right? And now they're going to lower the baseball back down. They're still supporting the baseball. So their force F is still directed straight up. But as they're supporting it, they're going to lower the baseball back down. So now the displacement vector is going to be negative, and the baseball ends up down here. Now the force and the displacement are in opposite directions, so this dot product is going to be negative. If we use this expression, we can see that the force has the same magnitude, the displacement has the same magnitude as it did in the previous case. It went up, let's say a meter, and then it went down, say a meter. The magnitude of each of those is the same. But what's changed now is the angle, phi, between the force and the displacement. Here they were parallel, so phi was 0. Here we have the force up and the displacement down. The angle between them, that angle right there, is 180 degrees. And cosine of 180 degrees is -1. So here we have negative work. And that means that this force is tending to slow the ball down. The ball wants to fall, we're supporting it, we're slowing it down. Third case. Let's suppose that we have this baseball, we're going to support it in our hand, but now we're going to walk across the floor with it. So here's our hand, here's the baseball. All right? And we're going to walk sideways with this thing. So the displacement vector is going to look like this. As we're walking, we're still supporting the baseball in our hand. We're still lifting up on the baseball. So now the force is perpendicular to the displacement, and that force doesn't do any work at all. Because this is a right angle right here, when we come to this, we have the force, same as before. The magnitude of the displacement, that could be the same as before. If this was a meter, we could walk a meter sideways with the baseball. But what changes is now the angle between the force and the displacement is 90 degrees. It's perpendicular. Cosine of 90 degrees is 0. So now that force does no work at all. Okay, so when you want to calculate the work, remember that it can be positive, it can be negative, it can be 0. The way you find out is to evaluate the two magnitudes of the forces and the angle phi between the force and the displacement vector. As we're doing all of this, in these three cases, there's another force acting on the baseball. That's the force of gravity. The baseball's weight is also acting on it. Let's go back and talk about the work done by the weight force as this baseball is moving. In the first case, the weight is down this way, mg, and the baseball is moving up. So the angle between the force and the displacement is now 180 degrees. And I'll write it in orange again. The work done by the weight, I'll call it the work done by gravity, is going to be less than 0. Gravity is doing negative work. As the baseball is being lifted up, gravity is pulling it down, trying to slow it down. In the second case, when the baseball is coming down, the weight vector is also down. And in this case, gravity is trying to speed it up. The force and the displacement are in the same direction. So the work done by gravity is greater than 0 in this case. In the third case, when we're going sideways with it, the baseball's weight is always straight down, and that vector is perpendicular to the displacement. Draw that better. And that means that, again, the work done by gravity is 0 because they're perpendicular. There are, by the way, 3 separate ways to have 0 work being done. Here was one case when the force and the displacement are perpendicular. That sets this term to 0. The other two ways are to make each of the other terms 0. If you have no force, of course you're going to have no work. But the other way is to have a force acting at any angle you want on an object, but the object isn't moving anywhere. If the object doesn't move, there's no work done. If you stand and push on a wall, you can be exerting a force, however hard you want, but if the wall doesn't go anywhere, you don't do any work. Work is only done on moving objects. If they're stationary, no work. All right, let's do another example. I'll erase this so we have room for the next one. In this one, I want to take an object and slide it down a bumpy track. So it looks like this. We're going to start the object from rest, and I want to know how fast it's moving at the bottom. So here's our object. It's a little box or whatever it is, right? And it's going to slide down this track. And I want to know at the bottom, how fast is it moving? Let's suppose that this bumpy track has a height of h and it has a length here, L. All right. We're going to solve this using the Work-Kinetic Energy Theorem, which tells me if I add up the work done by all forces acting on this box as it slides, that will tell me the change in the box's kinetic energy. Now, kinetic energy we did last time. Let me just remind you, kinetic energy is energy that's associated with mass and motion. It's half mv squared. When we want to use the Work-Kinetic Energy Theorem, we need to deal with all of the works that are done on the object as it's sliding. So we have to think, as the box is sliding down here, what forces are doing work on it? Well, there are two forces acting on it as it slides. There's its weight, which is always acting straight down, and there's the normal force. This bumpy track is supporting it. Let me draw those forces in orange. Suppose the box is right here. Looks like this. The weight is going to come straight down this way. And the other force is the normal force, which is perpendicular to the surface. So it's going to go this way. Now suppose we look at this again a little while later when the box is right here. The weight is still straight down, mg. And the normal force is perpendicular to the track. Now it's going this way. The weight vector never changes. It's always straight down. It's constant in magnitude and direction, which means that we can calculate the work done by weight using these expressions over here. Any of these. The normal force is different though. It's changing. It'll be changing in magnitude and direction. So the work done by the normal force, if we had to evaluate it, would have to be evaluated with this expression up here. But it turns out that we're not going to need to do that. We can just write down what the answer for the work done by the normal force is. Let's write this as the work done by all forces is the work done by the normal force plus the work done by gravity. And those will add to delta K. We can figure out what the work done by the normal force is. Because the object is sliding down the track, and the normal force is always perpendicular to the track, at every step along the way, the normal force is perpendicular to the path. There's a little ds element. There's a ds element. Everywhere along the way, the normal force is perpendicular to the motion. And that means that everything inside this integral is going to be 0 for the normal force. The normal force does no work on this object as it slides because the normal force is perpendicular to the surface and the object is sliding along the surface. So the normal force does no work. We can zero it out and be done with it. All right, let's deal with the work done by gravity then. As we go through this section, we'll come up with a number of ways of evaluating this. I want to do it here in the most fundamental way. I want to calculate the work done by gravity using this dot product. And I'm going to use this last expression here. The work done by gravity is the x component of the force times how far it moved sideways, plus the y component of the force times how far it moved up and down. Taking the usual xy coordinate system this way. So let's write the work done by gravity in vector form. It's the force, mg, dotted into the displacement, delta r. And that will equal delta k. Now what is this gravity vector? It's minus mg j hat. And we have to dot that into the displacement vector. Let me draw that displacement vector in red so that we can see it. It goes from the beginning to the end of the path. So that red vector right there is delta r, the displacement. Now, what does it equal? Well, the x component is how far sideways the object went, and that was L with an I hat. The y component is how far up or down it went, and this one went down a distance h. So we have minus, because it went down, h j hat. And that equals delta k. Now to evaluate this dot product, we need the x component of the force, which is 0, times the x component of the displacement. That's L. But that first term just gives us 0, because there's no sideways component of the force. For the y components, we have the y component of the force minus mg times the y component of the displacement minus h, and we find that the work done by gravity is mgh. Gravity does positive work as this box slides down this bumpy path. How much positive work? It's the vertical component of force times how far down the object moved as it slid. And that's going to equal delta k. Now, this delta k is kf minus ki. If the box starts from rest, if it's not moving here and just starts to slide, then half mv squared is 0 at the initial point, and all we have is 1/2 mv squared at the bottom. So that v is this one. It's how fast the object is moving at the bottom of the bumpy slide. We can cancel the m, which is interesting, and solve for how fast this thing is moving. The speed is root 2g times h, the height that the box fell through as it slid down this bumpy path. So there's a couple of examples of how we use this work-kinetic energy theorem. An important thing that we came across here was when you have a force that is constant, you can re-express the work done by that force as the force dotted into the displacement, which can also be written this way. If the force is not constant, you have to come back up and use this fundamental definition for the work. Okay, I will stop there and see you next time.